All right, this is section 6.3, Trigonometric Equations, Part 2. And there's not much different from this section to the previous one, 6.2, other than most of the examples here are going to have a double angle or a half angle in them. And so we need to manage that in some way. So let's look at our first example here. So you can see in this example that we have a double angle right here, cosine of 2x, and we need to find a way to write all of these in terms of a single trig function so we can isolate that trig function. So here, let's recall that cosine of 2x as an identity is 1 minus 2 sine squared of x. And therefore, if we have cosine of 2x equaling sine of x, which is the original equation, we can replace cosine of 2x with 1 minus 2 sine squared of x. And now we have everything in terms of one trig function, which is just sine of x. Okay, so that allows us simply to solve for sine of x, or isolate sine of x. This is a quadratic equation in sine. It perhaps would be a little bit easier if we let u equal sine of x, and that allows us to see this algebraically. So that would be 1 minus 2u squared is equal to u. And now you can move everything to the right-hand side and try to factor it. Okay, so this factors into 2u minus 1 and u plus 1. All right, so this equation splits into 2u minus 1 equals 0. And if we solve that equation, we get u equal 1/2, which means that sine of x is equal to 1/2 because u is equal to sine of x. And if we solve this one, we get u plus 1 equals 0. So u equals -1. And therefore, sine of x is equal to -1. All right, so the next thing that we want to do is find the angles between 0 and 2 pi that satisfy these equations. Okay, so let's take a look at that first one. Sine of x is equal to 1/2. Well, 1/2 is positive, so we're expecting an angle in the first quadrant and the second quadrant, because those are the quadrants where sine is positive. And we know that pi over 6 is a solution here. And we also know that 5 pi over 6 is a second quadrant solution. Sine of either of those will equal 1/2. And those are the only two from the unit circle. Okay, looking at the other one, sine of x equal -1, we know that there is one solution, and that's right here, which is 3 pi over 2. Okay. So now we'll just write down all the solutions. And that would be, we could say, of course, x is equal to pi over 6 plus everything coterminal to it. X equals 5 pi over 6 plus everything coterminal to it. Or x equals 3 pi over 2 plus everything coterminal to it. However, let's note that these three angles happen to all be perfectly evenly spaced. That is a gap here of 2 pi over 3. Okay, 120 degrees, which means we can actually collapse this into a single statement by just grabbing the most primitive solution, which would be pi over 6, and simply saying that x is pi over 6 plus a multiple of 2 pi over 3, stipulating, of course, that n is an integer. And if the question asked for solutions only in 0 to 2 pi, well, we can see that that would be pi over 6, 5 pi over 6, and 3 pi over 2. All right, in this example, we have cosine of a half angle, but notice there are no other trig functions in here, which means we don't really need to worry about this half angle until the very end. We can just think of this as 2 times cosine of stuff minus rad 2 equals 0. So let's just start by isolating cosine of stuff. All right, so we'll add rad 2 to both sides, and we'll divide both sides by 2. So we have cosine of stuff is rad 2 over 2. And again, even now, we shouldn't care that that stuff is a half angle or a double or a triple angle or anything that it might be. We're just going to answer the question, what stuff has a cosine value of rad 2 over 2? Well, we know that cosine of pi over 4 is root 2 over 2, and also there'll be a solution in the fourth quadrant, so that would be 7 pi over 4, whose cosine value is root 2 over 2. Now, it needs to be stressed that these are not x solutions, okay? These are actually what x over 2 is. These are the angles whose cosine is rad 2 over 2. We still haven't finished solving for x. Okay, which means that if this question had simply said, list the solutions from 0 to 2 pi, it would be wrong to just say, oh, pi over 4 and 7 pi over 4. Okay, so let's keep solving. What do we know? Well, we get to say that the angle, which in this case is x over 2, is equal to pi over 4 plus everything coterminal to that, and 7 pi over 4 plus everything coterminal to that. Notice we needed two different statements here because those are not evenly spaced around the unit circle. Okay, and let's stipulate that n is an integer. All right, that's what x over 2 is, but really we need to solve for x. So to finish isolating x, multiply both sides by 2. So on the left, we're going to get x, and on the right, we're going to get pi over 4 times 2, which is pi over 2, plus 2 pi n times 2, which is 4 pi n, and the other solution doubled will be 7 pi over 2 plus 4 pi n. All right, and that is the full solution set. Now, if the question said, find the solutions in 0 to 2 pi, well, if we look at our full solution set right above it, which ones of those land in the interval 0 to 2 pi? So certainly pi over 2 does. That would be the case when n is equal to 0. But if you added 4 pi or subtracted 4 pi from that, you would immediately be outside of 0 to 2 pi. Okay. So what about 7 pi over 2? Well, 7 pi over 2 is bigger than 2 pi, right? 2 pi is actually only 4 pi over 2. So this is much bigger, which means that it's not even in the range. So there's only one distinct solution between 0 and 2 pi here. All right? Whereas if you look at the diagram we drew, that seems to indicate there might be two solutions, but that's before we doubled everything. And this 7 pi over 4 got doubled away outside the interval from 0 to 2 pi. Only the pi over 4 managed to get doubled and stay within. That gave us the pi over 2 solution. Okay, so why don't we take a quick look at this one on death. All right, so in this one we have two different trigonometric functions, and which means we should try to find a way to use an identity or try to factor them apart, and factoring here will be very difficult. So let's just use an identity, And what we can do is factor 2 out of the first two terms here, because that's going to give us cosine squared theta minus sine squared theta. And we know that cosine squared theta minus sine squared theta is equal to cosine of 2 theta. That's an identity. So that means that this is 2 times cosine of 2 theta. And now we can just solve for cosine of 2 theta. So here we have 2 cosine of 2 theta is equal to -1. And so cosine of 2 theta is -1/2. Okay, again, we do have a double angle in here, but we're not going to worry about it until the end of this problem, like the last one. So let's locate the solutions. Cosine of some angle is -1/2. Well, we know there'll be a second quadrant result and a third quadrant result, because cosine of first and fourth quadrant produces a positive result. So, okay, we know that 120 degrees is a solution. So correspondingly over here, we have 240 degrees. Okay, now that's not what theta is, that's what 2 theta is. But let's write this down. The angle, which is 2 theta, is equal to 120 degrees plus everything coterminal, so plus 360 degrees n. Okay. At the same time, it's 240 plus everything coterminal to 240, stipulating, of course, that n is an integer. So now, dividing everything by 2 to isolate theta will give us our final answer. So we're going to get that theta is equal to 60 degrees plus 180, or it's equal to 120 plus 180 degrees. Okay, and that's our final answer. Now, what if the question asked to list the solutions from 0 to 360? Well, again, it's not just going to be 60 and 120. So both of those are solutions. However, notice that if we let n equal 1, we're going to get 60 plus 180 degrees, and that's still within 0 to 360. 60 plus 180 is 240. Okay, and we also get 120 plus 180, which is 300, and that's still within the range 0 to 360. But that's it. Okay, so at this point, these are what the n values are to produce each individual solution. Okay, and of course when n is equal to 2, you get 60 plus 360, which is too big, right? So these are the only 4 that we have. This is a complication that only arises if you're solving an equation with a multiple angle in it, like the last example with x over 2, or this example which had a 2 theta in it. All right. So if you are solving an equation with a multiple angle in it, then you actually have to find all the solutions before you list the solutions from 0 to 360, so that you make sure that you're getting them all. Okay? Because at this step in the problem, we only listed 2 angles between 0 and 360. But we know that there are actually 4 solutions between 0 and 360. Okay, for our last example, I actually decided to specifically stipulate that we only want solutions between 0 and 2 pi. And I'm writing it this way because I really want to emphasize how at this stage in the game, in order to list the solutions from 0 to 2 pi, we still have to go and list all the solutions first. Okay, so we just have to, no matter what, at this point, pretend like every question says, find all solutions. All right, so we'll worry about that at the end of this. So let's worry about just solving this algebraically here. Now we have a cotangent and a cosecant, and we know that cotangent and cosecant are related through the one coat in the closet identity. Okay, so let's try to find a way to use that. And what we're going to do is simply isolate one of these and then square both sides. So here's the original equation. Okay, so let's just move the cosecant of 2x to the other side. Okay, and now we can square both sides. So on the left, we're going to have cotangent squared of 2x, and on the right, we're going to actually have 1 plus cosecant of 2x, quantity squared, which needs to be FOILed. So cotangent squared of 2x is equal to 1 plus 2 cosecant of 2x plus cosecant squared of 2x. And now we should just convert this guy to cosecants. And we know cotangent, according to the identity above, is cosecant squared minus 1. Okay, so this is going to be cosecant squared of 2x minus 1 equals 1 plus 2 cosecant of 2x plus cosecant squared of 2x. Wonderfully, we can cancel cosecant squared from both sides of this equation. So what we have is negative 1 is equal to 1 plus 2 cosecant of 2x. So subtracting 1 from both sides, we get negative 2 is equal to 2 cosecant of 2x, and therefore cosecant of 2x is equal to negative 1. Okay, so let's draw quadrants here and place the solution on there. Now, where does this happen? Well, again, we're ignoring the fact that this is a double angle for now. I'm just asking the question, cosecant of what angle is equal to negative 1? Well, that would be 3 pi over 2. That's the only one. All right. Now, we did square both sides of this equation, so we ought to verify that this actually holds water in the original equation. So we didn't solve for x. We just solved for that green blob angle. So when that green blob angle is 3 pi over 2, does this equation work? Cotangent of 3 pi over 2 is 0, and cosecant of 3 pi over 2 is negative 1. So 0 minus negative 1, is that equal to 1? Yes. Okay, so the one and only solution we found does work so far. Now the question just said, find solutions between 0 and 2 pi. Okay, so like I said before, we still have to write all the solutions. So let's go and say, well, what was our angle? It was 2x, so that's going to be 3 pi over 2 plus everything coterminal to it. Now to isolate x, divide everything by 2. So we're going to get x is equal to 3 pi over 4 plus pi n. Okay, and that generates the full infinite list of solutions. However, the question did stipulate to list the solutions in 0 to 2 pi. So we're just going to list them manually. So we can see, of course, 3 pi over 4 is a solution. That's the case when n is equal to 0. What about when n is equal to 1? Well, 3 pi over 4 plus 1 times pi is 7 pi over 4, and that's also in the unit circle. Okay. However, when n is equal to 2, that's 2 pi plus 3 pi over 4, which is obviously too big. So those are the only two solutions that we have. 3 pi over 4, 7 pi over 4. And that's it.